Okay, so another sort of pretty much omnibus lecture on passive remote sensing radiometry and polarimetry with varying levels of detail or not. Okay, so this thing above me here, this is the sun, which is fairly important for all of this passive radiometry that we do. And I like this figure mostly because what you can see here are sunspots. And you can see that the sun actually dims by about a watt per meter squared. This was the first time that anybody had seen the total solar irradiance impacted by sunspots. And you know, since the sun is the engine that drives the planet, it's sort of nice to have the kind of measurements that tell you about that. And so I'll say more about the radiometry and how you measure the solar irradiance and how that plays into things as we go along. So I'm going to talk basic definitions and useful formulas following on from what Peng Wang presented. Fortunately, quite a few of them I'll be able to skip because he already covered them, which is great. And then I'll talk a little bit about calibration because I thought if we're talking radiometry and I don't mention calibration, then that's sort of really missing out on a substantial part of how you get where you're going. And then for remote sensing, mostly an overview of different tools that you can use in order to do different types of remote sensing. Okay, so ignore all the words at the bottom. They're in there mostly so that when I'm not here, you can read them. This again is coming back to what Peng Wang presented, what the radiance is. And you have energy per unit time, per unit area, per unit solid angle, per unit wavelength. And so this sort of ties into what Jeremy's going to talk about tomorrow with instrument designs and how much light you get. Delta omega times delta A is used in instrument design terms. It's known as the étendue and is basically the ability of an instrument to capture light. So it's basically the area of, say, the front mirror of JWST times the solid angle that it can see, and that gives you the amount of energy that you can capture from a scene. And then the other pieces are how long are you going to look at something and over what wavelength range. And that basically tells you how many photons you're going to be capturing. And that will give you the photoelectron count and thereby the signal to noise that you can reach. Okay, so coming back to looking at the sun, this is the total irradiance monitor, and I just want to point out that these are very similar instruments in some respects and not in others. So the total irradiance monitor has a very, very precise entrance aperture. They know the size of this entrance aperture to within 1 part per million, but it's only got 5 times 10 to the minus 5 meters squared, because you're looking at the sun, and it's a nearby star, and it's really bright. And as a result, you only need about 100 seconds of integration. The solid angle is actually quite big. It's half a degree. It's the full solar disk. And it detects the entire solar spectrum effectively from around 200 nanometers out to 100 microns. So that's one instrument. And then, of course, there's James Webb Space Telescope. And it's very different, right? 33 meters squared mirror. The deep field integrations that you saw on the news were on the order of a day. And they have various different spectrometers with different spectral resolutions. But obviously, the angular resolution is really fine. It's 0.1 arc second. But in all of, that was interesting. In all of this, you're sort of always going back and looking at how does that play into the radiance and what am I capturing with my instrument design. So a couple more basic definitions. Peng Wang covered the fluxes. All I wanted to say about this is the planar irradiance is all about energetics. It's about how much can you heat something if you have a net irradiance through a given depth in the atmosphere. So that tells you how much your atmosphere is going to heat up. And so planar irradiances are all about energetics. And then the scalar irradiance, it's not about energetics, it's about how many photons are going through a given volume. And so you have here this photosynthetically active radiation from 400 to 700. It's kind of arbitrary, really. A lot of people don't use this anymore because the way in which different plants react to radiation will have different action potentials across the spectrum, so people will integrate over different wavelength ranges. And it's just counting the number of photons per second that are going through a given unit area. And it's also something that's used without this particular wavelength integral. Actinic fluxes are the same kind of thing, because when you're doing chemistry, you also don't care about whether something is going through a flat area. You care about whether it'll hit a molecule and cause them to do something. Okay, and then, so see, Peng Wang did the really complicated bit where everything's interacting with matter, and there's a really complicated equation. But if you get rid of all the matter, then the radiance in free space actually doesn't change along a ray. So you have this without all the other stuff, and you have a constant radiance along a ray. And then you can have the irradiance is integrated over a solid angle. Solid angle is the area divided by the distance squared from something. So you have this classic radiometric thing where, and that dA shouldn't be there, where the radiance is proportional to 1 upon r squared. And this is really just that if you have an isotropic scatterer, an isotropic source, then you have constant energy going through a given area, like the 4 pi r squared of a sphere. And obviously, if the sphere gets bigger, then the irradiance through any given part of that area drops as 1 upon r squared. Personally, I'm not awfully keen on this because things like this right there, that's not in the far field. That's not going as 1 upon r squared right here. And so it's fine if you're talking about the sun. It's okay if you're talking about incoherent lamps. But just be aware that it might be something that's in radiometry, but it's not something that really should be applied to coherent sources. And then this was what I was saying about the étendue. It's conserved. So the key thing to remember is if you screw up the front end of an optical instrument, you're done. There's no way to fix it. So make sure you design the front really nicely. And then if you have even a halfway decent design at the back end, you'll preserve your étendue and everything will be good. But get the front end right.
Can I just ask what you mean by front end and back end?
So the front end is like JWST, right? The front end is that honking great primary mirror and the secondary mirror. And that's the front end. That basically defines the area of detection and the solid angle that you're detecting. And then in the back end of JWST, they actually have pickoffs going to at least 3 or 4 different lines of detectors. And so those are getting there's a split, but they're also effectively getting the same étendue going into them, although you've often done a spectral split in JWST. They have mid-infrared and infrared. But it's the front end is in JW. So let's go. So the front end in a Gershon tube, which is this thing. So this is a really, really simple front end. The front end of this is how big is the aperture, and then how big is the detector back here. The combination of that aperture and that detector determines what the area and the solid angle that's subtended are going to be doing for you. And obviously this étendue, that's it. It's a tube. That's all she wrote. And although this is something that's shown in ocean optics and people are like, nobody really flies one of those, this is a Gershon tube, right? And it's the most accurate solar irradiance measurement that's ever been made. They measure solar irradiance to 10 parts per million because it's all about having a precision machined, NIST characterized aperture at the front and an incredibly good detector at the back. And then at the other end of the spectrum, we have a relay telescope. And in some ways, JWST is a relay telescope, but we're going to talk about OCI now because OCI is actually a rotating relay telescope, which defines the étendue of the system, with not anything like this at the back end of a relay telescope. And Eric will be showing you there's a lot of very complicated things going on at the back end of that relay telescope. Splitting light, spectrometers, fibers, fiber coupling, lots of stuff going on hidden away back there. But basically a well-collimated radiometer and a Gershon tube, they actually do exist out in the real world, and relay telescopes are actually really common in satellite instrumentation. Oh, and then the other thing I wanted to comment on was different detectors. Okay, so OCI is got CCDs and it's got photodiodes, and those are basically photon counting to some extent. They're getting photoelectrons that are generated by the incident radiation, so you're counting photoelectrons. This TIM instrument, all you do there is you have the sun come in and it heats something up, and you compare it to something else that you know what temperature it's at, and it's in a reference cavity, and then you put power into one of them to make them exactly the same. And so it's really, all you're doing is what's called electrical substitution radiometry, and we are actually really good at measuring electrical power, better in many respects than optical power. And so that's why this instrument is so accurate in its measurements of the sun. It's because it uses electrical substitution radiometry and measures the power that you're putting onto that detector really, really well, so it can compare electrical power to solar power very, very precisely. Yeah, and then if you've got a lot of money and can put a satellite somewhere where you can actually get the detectors down to a couple of millikelvin, you can actually count photons and know what energy the photon is at the same time, which was mind-blowing when I first saw these results. This is the sort of thing that you're only going to use if you're trying to look at exoplanets, because it's such expensive technology that's so hard to cool. But it is pretty cool to be able to detect the energy of a single photon. And they do this by having light collide with microwave detectors. And so the size here is basically the number of microwave photons that a given photon is kicking into the detector. So that's just something unusual that I thought I'd throw in. And this is something that's not unusual. This is a lake. I'm going to ask you questions about this later, so just remember. But I threw this in because this is a lake with some wimpy clouds, and it's sort of, with all the light on it, it's not actually looking particularly good up there. It looks much nicer here, but anyway. And this is a polarized lake. So a couple of things. So I threw this in because it's like Stokes parameters and all that. What's the polarization going to be doing for you? Well, clouds are black, obviously, and the sky's red. And the sky's red because you get more scattering in blue wavelengths, and polarization is primarily generated by just one or two orders of scattering. And the degree of linear polarization is the ratio of the polarized to the total. So the polarized is pretty much done after two scatterings. If the total keeps on increasing, then the polarization goes down. And so you end up with the sky looking red because the blue sky is brighter, and the degree of linear polarization in the blue is lower. So red sky at night, polarimeter's delight. And Peng Wang showed this, so we'll skip that, and we'll skip that. And okay, so this I did want to comment on. Okay, so Peng Wang showed the rotations in and out of plane and all that, which is great. One thing to be aware of, as Peng Wang pointed out, is our instruments will be reporting I, Q, and U, the Stokes parameters, in the meridional plane of the instrument. that is not always the best plane to look at it in. And the reason for that is, say you have, almost all natural particles will have a Muller matrix that looks like this. Officially, it's for statistically isotropic mirror symmetric random particles. But just think natural particles. They tend to have this block structure. And so if you look at how that block structure gets propagated through the rotations, if you are in the meridional plane, then you'll have something here, here, and here. And the variation of these two will depend on the orientation of the satellite with respect to the sun. And it's just entirely arbitrary what's going to happen then. So what you want to do is rotate back into the scattering plane so that what you see is the 1,1 element and the 1,2 element. Because a lot of times the scattering is going to be dominated by low-order scattering for the 1,2 element. And so U in the scattering plane will be very small. And an example of that is here. So this is taken a couple of 100 meters above Mexico City, right next to the busiest runway in America, in the Americas. These are cars. And this is Q and U rotated into the scattering plane. And this is Q, and this is U. And so that's just one of the reasons why you might want to rotate into a scattering plane, so you sort of can get rid of things that are of no interest and actually understand how something is varying and get an idea of what's going on. And in this case, this is just showing that the polarized scattering of the surface in Mexico City is actually pretty much gray. That's wavelengths from 410 nanometers to 865 nanometers, atmospherically corrected, and they're pretty gray. So that was a nice thing to get from flying very low over Mexico City, looking through the pilot's window and seeing the planes land at Mexico Airport, which was a little daunting at times. Okay, and then how do we measure the Stokes vector? So this is the classic thing you'll see in textbooks. The ocean optics book, they almost all have this, where you have a retarder and you have a polarizer, and then you can put it in different orientations and measure I, Q, and U. So the intensity is 0 and 90 degree polarization rotations summed. Q is 0 and 90 differenced. U is 135 and 45 differenced. And V, you have to actually have a retarder in. And people, again, you know, I wanted to make the point that while this is a textbook kind of thing to do, my polarimeter actually does do that. So we actually measure polarization at 0 and 90 degrees, 45 and 135 degrees, take those differences, and you get I, Q, and U. And in many respects, HARP2 does a very similar thing where they've got 0, 90, and 45, and the differences that you have to take to get I, Q, and U are a little different, but it's basically the same kind of thing. So the textbook example actually is at least related to how all of these instruments work in their measurements of I, Q, and U. And I'll go past that because that's a lot of words. You by all means read that if you download this. I just wanted to make the point that, and this is something Peng Wang also brought up, the radiative transfer equation is an entirely phenomenological equation which until quite recently was not really tied properly to electromagnetic theory and Maxwell's equations. And my colleague Michael Mishenko wrote a book on how you can do that. And if you really like tensor calculus and dyads and dyadics, I recommend looking at the chapter on the derivation. Otherwise, just take it from me that there is now a good solid tie between electromagnetic theory and Maxwell's equations and the radiative transfer equation, which is quite strange because Maxwell's equations are wave equations, and the radiative transfer equation is really an equation for the propagation of particles. So it's kind of interesting that you can take a wave equation, scatter it around a lot, and end up with a transport equation. And then this is the sun again. I just thought I'd show a couple of examples of polarization. This is looking at the Zeeman effect. This is actually the circular polarization of the sun. And it just shows how the magnetic field of the sun varies across the disk. For what we're looking at, we're only interested in the disk-integrated properties of the sun. And these all average out to 0 to within 10 to the minus 5 over the disk of the sun. So that's what we're using as our source. And then the other thing I wanted to comment on, and Peng Wang's exactly right about humans really almost never being able to see polarization. You know, we're in the visible spectrum. But actually a lot of animals, birds, insects actually see into the ultraviolet, and they also see polarization. So I think PACE is really looking at the world in a much more natural way than just doing it the way people do. We've got that UV and we've got that polarization, and that's how much of the living world sees the world. And then last of the asides, since we're going to be talking remote sensing, I work at GIS, which is in New York City, which Jim Hansen ran, was the director of for many years. This is remote sensing of Venus. This is observations from ground-based telescopes. And these observations were used to determine that the refractive index of the clouds was about 1.45, and the size was about 1.1 micron, and that the Venus atmosphere is made up of sulfuric acid clouds with small droplets, which was an amazing inference from ground-based telescope measurements of a planet. Okay, so talking about radiometry, so the reference for all national standards labs these days is an electric substitution radiometer, a cryogenic one, which measures the electrical power and matches it to the radiative power. You can then trace that to reference photodiodes and filter radiometers, and then to a black body, and then to a standard lamp. And as you can see, all of these uncertainties are increasing. The thing that most of us can get access to is a standard lamp, and you know, the claim is it's 0.7% uncertainty for a standard lamp. Most people who've used them would not believe that. You're hard pressed to get to 3% if you're using standard lamps. And the way in which they're used for irradiance, you just have an alignment laser, a lamp, and you put your radiometer in front of the lamp. And that's looks really easy, but it isn't actually as easy as it seems, because getting that lamp aligned and getting all these baffles properly done so that you don't actually have stray radiation is hard work when you've got a kilowatt coming out, and most of it is not actually calibrating your radiometer, because it's that 1 upon r squared. It's going everywhere, all over the lab, and heating everything up. The other thing you can calibrate is a radiance. So you use the lamp to illuminate a plaque like a piece of spectralon. And then you use a radiometer to look at that plaque, and you can calibrate the radiance, which is fine. The only issue with that is you just get one value of radiance that you're calibrating to, unless you can, in a very controlled way, move this distance to get multiple values. So it's a lot of hard work, and you get 1, maybe 2 radiance values. So if you're lucky, you can find somebody with a really nice integrating sphere with lots of lamps, and you go over there, and it takes you maybe an hour to get 6 or 9 lamp levels. But if you can't find somebody to do that, you're stuck with this kind of thing. And lastly, and this is what was used to calibrate OCI, is to use those calibrated photodiodes, a really fancy laser system that you can scan from 320 nanometers all the way out to 2300 nanometers, and you use the traceability of the absolute standard to the calibrated photodiodes to provide a radiometric, spectrally scanned calibration, which is absolutely amazing. It's just they're really expensive and it's hard to get time on them. But if you build an instrument and you really want to calibrate it well, and you can find somebody at NASA to work on a project, we have a couple of these systems at NASA, and it's really worthwhile. My instrument had what we thought was an out-of-band leak, but we'd never been able to find a good enough system to test whether it actually existed or not. And by doing the calibration with this laser system, we were able to completely rule out the notion that there was any out-of-band leak there. So it is a really nice capability, and I just thought you should be aware of it if you actually build instruments yourselves. Okay, so remote sensing. This is, I think this is Apollo 11, right? This is the Earth. People talk about all the other planets, but our planet is actually the most visually spectacular of all of them, I think. With the blue skies and the clouds. And obviously, these are the things that we want to do remote sensing of. And to do the remote sensing, we need models of all those different pieces. And this is a nice schematic that I pulled from NASA RSET. There was a list of different resources available, and those RSET packages are actually quite helpful. They have some nice summaries of how to do things, and this is a nice one showing the sun, the atmosphere, and listing all these different surfaces, and then you've got your satellite up there. And then this notion of you're going radiance to radiative transfer to retrieval, and then these geophysical parameters that Lorraine was talking about. So remote sensing is taking the remotely sensed, potentially polarized radiance field, including its spectrum, and then inferring the distribution of scatterers and absorbers and their sizes and compositions that generated what you're looking at, whether that's the atmosphere or, obviously, ideally for Jeremy, the stuff in the water. That's his baby. My baby is the atmosphere that he wants to get rid of, which is 90% of the signal. So in order to do that, you do need to have these models. And so it's great that Peng Wang could go through and talk about all these different ways of calculating the single scattering properties, because you want to be able to take a particle size, shape, and composition and give yourself optical properties. And then if you have a concentration profile, then you can calculate, the distribution of radiation. And this is just a gratuitous picture of a NASA ER2 plane climbing over the sand dunes in Namibia. And I just like it because I visited Namibia and the sand dunes were fantastic. So. And at 3:30, it seems appropriate to put something like that in, especially since the next slide is this one. Okay, so I am not going to go into detail on minimization methods or how you would go about minimizing this equation, because there are multiple entire books on just solving this equation. So I just wanted to talk at a very high level about what we're doing when we do actually solve this equation. So this is the uncertainty in your measurements, sort of the covariance matrix of uncertainties in your measurements. It also should include forward model uncertainties and everything else that you're uncertain about. And this is the difference between what you observe and the model of the atmosphere that you have. And then this is some side constraint that you put on so that when you try and match your radiances to your model, that you don't come up with some really stupid solution that isn't in any way physical. And I'll just give one example from when I was doing this, one of the retrievals that I was trying to do that completely blew up, and that's why you really need something like this, is if you are doing an aerosol retrieval and you assume that the aerosols are mixed exponentially from the surface up to some height, and you allow that height to change as a retrieval parameter, and you have a smoke plume that is actually at 4.5 kilometers, that's 50 or 60 meters thick, then your model does not match your observations. And you can end up getting a solution that just continuously walks away, increasing the optical depth and increasing the imaginary refractive index, because your physical model does not match with the actual real world that you live in. And so those are the kind of things that you can deal with by having strong constraints on priors, and also by making sure that you do the best job you can on creating the physical model that you're going to use to model the world. Like, for example, you definitely want, if you're a passive remote sensing guy, you definitely want a vertical profile that allows the aerosol to become detached from the Earth's surface. And then this is just comments on Levenberg-Marquardt is you stop this thing getting too big. So once I did that to my retrieval, it stopped the refractive index walking off into strange places that it shouldn't be. And then eventually I found a LiDAR curtain that showed I got this incredibly thin layer. And then Levenberg-Marquardt is another one of these iteration schemes. It actually puts constraints on how big the steps you take can be, so that when you start off this kind of iteration, you don't walk off somewhere where you can never return from. And so this is an example. I just thought I'd throw this in from my colleague Jacek Chowdhury's work. And this is the sun glint, 410, 470, 865, and then 550 and 670. And this is total reflectance, polarized reflectance, and degree of linear polarization. And the point being that by the time Jacek adds in his case 1 ocean for these case 1 waters, you can actually match the measurements and the observations to within the uncertainty in the measurements, to well within the uncertainty in the measurements. And so that's sort of where you want to be. You want to match your measurements and then have retrieved optical depths. These are 2 different days. And then single scattering albedo, where AeroNet didn't agree with the in situ, and our estimate was sort of right in the middle between them. And trying to decide who's right between the in situ and AeroNet is actually not that easy, because in situ measurements of aerosol absorption, which many of you may not care about, in situ measurements of aerosol absorption are difficult, and the instrumentation that's used to make them is probably about 40 years old at this point. And aerosols can have very, very different amounts of absorption. The classical example being Tammy Bond, who's one of the leaders in the field of quantifying absorption by black carbon, has this great clip from a movie where there are 2 engines pulling a train. Both they're coupled together. Both engines look exactly the same, and one has white smoke and the other has black smoke. And it's sort of like, well, what are you going to do when you have 2 almost identical engines, obviously burning different fuels, and the absorption in those 2 different aerosols is completely different. So it is one of those things where if you're doing remote sensing of aerosols, you do want to retrieve the single scattering albedo or the fractional absorption of the aerosols if you possibly can. And I thought I'd just comment on the definition of the aerosol optical depth. So Peng Wang gave the mathematical definition, but I like to think of it in another way. So the optical depth, it's the cross-section of aerosols, whether that's extinction or absorption. It's times the number concentration. So that's the attenuation per unit distance that you get. If you then multiply that by some finite depth, that's basically the number per meter squared multiplied by the cross-section. And so what that is really it's the fraction of the sky that is covered by scatterers or things that are extinguishing things. So to a large extent, at least for aerosols, you can think of the optical depth as a fraction of the sky that is covered by the aerosols. So, the optical depth is a nice mathematical thing, but sometimes it's helpful just to think of it in more simplistic ways as like just the fraction of the sky that's covered. Because then once you get to an optical depth of unity, you know that that notion is completely breaking down and you're definitely going to be having multiple scattering. Go ahead.
Does that mean the vertical fraction or the fraction x-y?
It's the fraction, if you're looking straight up, it's the fraction of the sky that's covered by the particles. And that's sort of integrated all the way through. So, aerosol optical depths are often a tenth. So the implication is that you have 10% of the column that you're looking through has aerosols covering it, and that's integrated all the way through. Oh, okay. So, Peng Wang and Lorraine both put spectra similar to this. So we're not going to talk really about infrared remote sensing. This is the solar spectrum. This is the Earth spectrum. Lorraine talked about the history of atmospheric remote sensing. These spectra are from 1970, so that's over 50 years ago. These spectra are from Nimbus 4 Iris. And the only spectra from satellites that go beyond 20 microns that are downward looking that have been made almost continuously since Nimbus 4 Iris stopped are actually spectra of Mars, not the Earth. So we have great spectroscopy of Mars. We have really good spectroscopy, sort of shortwards of 20 microns now of the Earth with the atmospheric sounders that do all the weather, that are on all the weather satellites. But the reason I raise this is that once you get beyond 20 microns, you are in a spectral domain known as the dirty window. And the dirty window gets filled up by water vapor absorption. And the reason this is of interest to me is because it's of interest to climate, and I work at a place that's mostly about climate modeling. Because the dirty window is clean where you don't have much water vapor. You don't have much water vapor at high altitude and in the Arctic and in the Antarctic. And so one of the reasons why there is accelerated warming of the Arctic, the Antarctic, and also high altitude areas is actually because of this dirty window closing as a result of increasing water vapor in the upper atmosphere. And so this thing here is just showing that as you increase by 10% or 20%, you're decreasing the radiation that's going out of the upper troposphere. Or in the case of the Arctic, the amount that's going out of the surface. So I just thought I'd comment on that as a climate-related thing. And then the other thing was that I was reminded of was Lorraine showed those great pictures of Pinatubo, of the eruption with that huge aerosol load. Climate modelers are not allowed to do experiments on the Earth, right? We're not allowed to set off volcanoes. But when they do happen, they are an incredible tool to evaluate whether climate models work properly. And so Pinatubo was probably, it was a total disaster for tens of thousands of people in the Philippines. And I've been there, and there are like 60-meter high banks of ash when you go up the river. But for the climate modeling community, it was an incredible opportunity to evaluate whether the models were working properly, both radiatively and also in their feedbacks, particularly with regard to water vapor. And so Pinatubo and the remote sensing that allowed the modelers to know how much aerosol was in the stratosphere was a fantastic resource and has been used many times over the last 30 years. So thanks for reminding me about Mount Pinatubo. I had a great hike up there as well. Oh, any questions?
I have a question.
Yeah.
Since Pinatubo erupted, have there been other large enough eruptions that they've used those as indicators? Like,
No.
I can't say the one in
No, I can't either.
No.
I can't either.
I mean, that was spectacular and huge, obviously, but some of the more recent ones have been
Yeah, so
getting closer. So I'm just curious.
yeah, no, it's a really good point. So before Mount Pinatubo, the previous one that was also really big was Mount Agung. I think that was 83. So yeah, so
I'm thinking about, and again, I can't say, it was in like 2010.
yeah, so although that impacted air traffic, it wasn't big enough to impact the radiative budget of the Earth in a significant way. And one of the reasons that happens is the ones that actually generally have the biggest impact are those that happen in the tropics, because once the material gets lofted into the tropics, it tends to stay. In mid-latitudes, what you find is that these volcanic eruptions, you get an eruption, but the material doesn't actually stay in the stratosphere for as long as it does when it gets pumped up into the tropical stratosphere. And also, Agung and Pinatubo were just orders of magnitude bigger than the one that we won't name.
Yeah. Well, that's true. Yeah.
But yeah, thanks for the question. Yeah, there are quite a lot of satellites that do look at them, but they're more looking at the amount of sulfur dioxide that comes out of them and things like that. And obviously, ideally, you want to be able to do human safety, like tell people when they can fly planes, but LiDARs are great for that. It's quite a lot harder to do with the sort of instrumentation that's up there right now. Okay. Back to absorbing gases. Okay, so this is higher spectral resolution than the one that Peng Wang and Lorraine showed. This is still only at 1 nanometer resolution. So within each one of these 1 nanometer bins, there are many lines. And I just thought this was a useful thing to stick in the slide package for you, because a lot of people don't know where all these absorption features are. So the main ones to consider are, there's a nice optical depth. So there's a nice window here. This is where OCO is doing CO2 remote sensing. This is a very strongly absorbing water vapor band at 1900 nanometers. This is the 1378 one. These two are generally used by remote sensing people to look for cirrus clouds, because there's so much water vapor absorption that you can't see the lower atmosphere. So the surface is black and cirrus clouds show up really well. Satellites use this one. In reality, this one's probably better, but we've started using this one, so we're going to keep on doing it. This is just my entirely bigoted opinion, and you're welcome to ignore it. I agree with Steve Ackerman from the University of Wisconsin. The reason that we like this one is because in this one, ice and snow are really strongly absorbing. And what that means is that when you're over the Arctic or the Antarctic, where there's not very much water vapor, the surface is still pretty black. Whereas this one, the ice and water don't absorb as much, and so the 1378 nanometer band is not very useful over the Arctic or the Antarctic, because not much vapor and the surface is still kind of bright. And then, okay, so I think, did you ask the question about gases and how you pick them apart? Okay, cool. So these are measurements from TROPE-OMI, and this this is in the part of the spectrum where methane has lines that are quite a lot stronger than the water vapor lines. And so when you have an instrument that has a spectral resolution that's on the order of 1/10 of a nanometer, you can actually differentiate between the water vapor and the methane really well. And what that allows you to do is detect methane. So this is a detection of methane coming out of a landfill. And, you know, Tropomi has like 5-kilometer resolution. And so the nice thing that they've done is they've teamed up with a Canadian group which has the greenhouse gas satellite, which has on the order of 25-meter resolution, but only 50-kilometer size of observation. So it would be almost impossible to find leaks if all you had was this instrument that can only see 50 kilometers at a time. Tropomi sees the whole world every day, and they can detect leaks reasonably well. And then they can tell these other guys, okay, there's a leak here, and then they can go in and they can image it at 25 meters resolution. And what that allows you to do is find strong sources of methane. And they've been finding all sorts of leaks in pipelines in Russia, also leaks associated with different facilities in the US and the shale gas. So it's a really nice capability to be able to take this kind of spectroscopy to get methane and go from the large scale with Tropomi to the fine scale with the greenhouse gas sat. And then this is a little bit more spectroscopy. So this is the oxygen A band. I apologize for the figure. It looked better when I was looking at it before. And this is just showing that if you make the ratio of the reflectance in one of the other wavelengths to 758, which is non-absorbing, then when you have no cloud, you get more absorption because you're seeing the entire atmosphere and seeing to the surface. You stick a cloud in, the cloud cuts off atmosphere, and so you can use this to do the cloud top pressure. And Andy's going to say more about this. This is one of the products from OCI. And he'll be here on Wednesday and doing that in lecture 10 with Lorraine, right? And this figure again, so this is clouds. And this is Rayleigh scattering. So like Peng Wang said, this figure does cover both clouds and Rayleigh scattering. And what he was saying about not using two is actually the most true around here, and this is actually around 5 microns. So real water droplets in real clouds, the extinction efficiency is not 2, and you make the biggest errors for the smallest drops. The bigger drops, you're up here, and you shouldn't do it, but it's better. And then I just thought I'd throw in a few examples of how this sort of thing shows up. Obviously, the Earth with, Rayleigh scattering we've talked about, white clouds, Rayleigh scattering, me theory. This is after the Pinatubo eruption, and this is mostly about scattering all the blue light away so that all you're left with is the red light, so you get this beautiful sunset. This is also the same kind of thing. This is dust on Mars, and the dust is absorbing in the blue, and so by the time the sun gets through all the dust, you have a very reddish haze that you're looking at. Oh, thanks, Peng Wang. And then this one is an oddball. I thought, when I grabbed the picture, I thought, well, that's got to be due to Rayleigh scattering because it's blue, right? And that's not true. This is actually caused by methane clouds on Neptune. And the methane clouds have a minimum in their absorption right around 410 nanometers. So that's why this is a deep blue color. It's because methane doesn't absorb much there. And the methane absorbs almost all the red and green radiation. And this is the figure that Lorraine showed. So if you're doing remote sensing of clouds, really what you're using is clouds are white, so for the most part. So what you're using is the fact that ice, which is the solid line, and liquid water, which is the dot dash line, they absorb at from 1.5 micron is the peak, and 2 micron. And if you put spectral bands, so this is why they like the 1.88 micron for Cirrus remote sensing, because this is ice and water absorption, and this is my 1.88 micron band. This is the 2.26 micron bands, very similar to what's on the satellite instrument VIIRS. This is 1.59. This is very similar to MODIS and VIIRS. And what you see is that ice is more absorbing than water in one of them, and water is more absorbing than ice in the other. So what that allows you to do is differentiate between ice and water, even if you have a single look at the cloud using the shortwave infrared. And this is the kind of thing that we're going to be doing with OCI to do cloud phase, because as Lorraine pointed out, we don't have an infrared instrument to tell us what the cloud phase is. Although infrared instruments also have issues with detecting cloud phase, because while ice forms at 0 degrees C, you can get supercooled cloud droplets down to minus 20 degrees C easily, and the homogeneous freezing point of water is minus 32 degrees C. So you can get liquid water down to minus 30 degrees C. It's very, very rare. But minus 20 degrees C in the Arctic and Antarctic at the top of clouds is actually quite common. So it's actually really hard to use a thermal measurement to do the cloud phase, because you're at minus 20 degrees C. It's still liquid, but it's going to look awfully cold. So anyway, where was I? Yeah, so this is the imagery index. So what Peng Wang in the previous figure was showing was the extinction cross sections pretty much proportional to twice the area. The absorption cross section is proportional to the volume times the imagery index divided by the wavelength. And then this formula is sort of getting a bit cut off. But basically, if you form the ratio of the absorption cross section to the extinction cross section, and basically that's the fraction of light that's going to be absorbed per collision. It's the ratio of the volume to the area times the imagery index divided by the wavelength. And this volume to area is 2/3 of the effective radius. And that's why you have the effective radius here for this absorbing band. As the effective radius increases, you're getting this fractional effective radius times imagery index is increases the fractional absorption, makes the reflectance decrease. Whereas the non-absorbing band, it's all about how optically thick it is. So it doesn't care so much about whether the cloud's absorbing or not. And so you can pick these wavelengths to be good for liquid clouds and ice clouds, and you can do this same thing for both liquid and ice clouds. And then if you've got a polarimeter, like Lorraine's polarimeter, you can look at cloud bows. And, I guess Ivona was putting together a playlist, and we got to have Joni Mitchell's cloud from both sides up, right? Anyway, so this is 865 nanometers. This is showing how the cloud bow moves with droplet size. And then all this funky going up and down stuff, that decreases as the size distribution width increases. So when you have a wide size distribution, you get rid of all these bumpy bits, and you just have the cloud bow left. And just to point out that these are some measurements from my instrument, just showing a fit between a retrieval and cloud bow. Cloud bows are ubiquitous in polarization. If you can see a scattering angle of 145 degrees, you will always see a cloud bow if there's a liquid cloud there. So whereas we're not used to seeing rainbows, Satellites are actually in a geometry where they see this kind of scattering angle quite often. And so the HARP-2 instrument is going to see lots and lots and lots of cloud bows and do lots of beautiful size distributions. Yeah, this is a bit technical. Just the point is, the cloud bow, so this is the cloud bow. The cloud bow comes from the top of the cloud. The Nakajima King bispectral thingamajig comes from all through the depth of the cloud. This is showing how if I change the droplet size by a certain amount in microns, the reflectance contribution will change through the depth of the cloud. So it's basically a weighting function calculated through the cloud. And so when you're trying to combine OCI, so if we try and combine OCI and those kind of shortwave infrared measurements with the polarization measurements for HARP, we are actually probably going to have to do a more sophisticated model than is typical, because the droplets at the bottom of a liquid cloud are always much smaller, unless there's precip there, than at the top of the cloud. And so usually you have to have an upper cloud layer and a lower cloud layer if you're going to combine the two together. Oh, I got this. This is advertising for Lorraine. This is HARP CubeSat data, because obviously to get that kind of measurement, those kind of measurements of cloud bows, you've got to have that multi-angle thing. And so this is just showing that, you know, they did this for Polder, but for Polder they don't have as many, they don't take pictures as often. So they would only get about 14 view angles for any given ground scene. So they could do cloud bow retrievals for like 100-kilometer megapixel, but not for anything else, whereas HARP will be able to do that at a pixel level at the 5-kilometer scale. So that's really, really exciting. And then you can actually do size distribution retrievals from cloud bows. So when you're using the absorption, you really don't know anything about the size distribution width. However, you can actually, if you do the math, you can realize that the cloud bow is actually tied by a transform very much akin to a Fourier transform to the size distribution. And so you can take that cloud bow measurement and convolve it with a kernel that turns the cloud bow into a size distribution. And so this is just showing some examples of size distribution retrievals from my instrument and then in situ. So you can see that the remote sensing is actually capturing this growth of the size distribution. And that's actually, for atmospheric remote sensing and understanding what's going on with clouds, that's actually really important. Because when you have narrow size distributions, which are actually very, very common, far more common than this kind of thing, droplets, it's really almost impossible for droplets to collide. They'll just go right past each other. To get droplets to collide, you really need them to have different sizes. And so once you create this quasi-drizzle mode, you're about to start forming a lot of drizzle, and that cloud will rain very quickly. And so understanding how common this is sort of a really helpful thing for understanding cloud physics.
Is that because there's just that little hump on the right side of the peak? Is that what you're saying?
Yeah, so this little hump here, that's really important. I guess I should have put in the typical size distribution. So typical cloud top droplet size distributions would be the width of this spike. They're really narrow because what happens is you start off, you nucleate a whole bunch of drops, and then as you lift them, you condense water onto them. And as you condense water, the smaller ones catch up to the bigger ones, and you just continually narrow the size distribution until you get to cloud top. So by the time you get to cloud top, you're generally super narrow, which is typically a problem in terms of modeling how clouds form rain, because once you're that narrow, you can't. The collisional coalescence kernels are really inefficient for those drops to collide with one another. And so clouds will not form any drizzle for extremely long periods, and that's observed in nature. Whereas a lot of models will actually start trying to turn it into rain too soon. And what you really want to know is how often does this kind of process happen and under what circumstances? And it's really helpful to be able to do that with remote sensing, because in situ might be good, but it sees such a tiny part of the world. So having HARP2 to do this kind of thing will be a game changer in terms of seeing this all over the world. And then the horrible particles that are not spherical. So spheroids are a commonly used model for scattering by dust, and they seem to work pretty well for the passive remote sensing. This is just showing the only color that's wrong in between the different labels. This is a sphere, this red one, and over here it's orange. But this is just showing how all these different scattering phase functions for all these different shapes are different. And so if you're doing remote sensing, you actually need to be able to diagnose between the different shapes that you have, or at least have a model that allows you to deal with something like dust. And then there are even things like sea salt that up to 70% relative humidity might not be particularly spherical either, which is actually observed. You can see this in LiDAR returns when you have relatively low humidities where the salt is not deliquesced, so you don't have spheres. So spheroids are a nice proxy for dust. For remote sensing, we also need to figure out what we're going to do for ice. Yeah, I didn't have a picture. Okay, so ice. Ice comes in lots of shapes. They're Droxtals. I mean, this is just showing from Ping Yang's group. Columns, bullet rosettes, Droxtals, aggregates. So many shapes. It's like a bestiary. You don't know what to do with it. But what we found is that, at least for remote sensing purposes, all of these different things look like hexagonal columns or plates with different aspect ratios and different amounts of roughness. And so what this is showing is how well can we match the forward scattering caused by really complex ice particles with a really, really simple ice particle, because that's the really main thing we want to get out of remote sensing of ice clouds. And so this is showing that a simple model actually matches almost all of the really complex models. So we now have a model for ice that it varies continuously with the aspect ratio of the ice and its roughness, and allows us to do a retrieval of the ice shape. And the reason that that's a good idea is because when we use that method, you find that the asymmetry parameter, which is the weight of how much forward scattering versus back scattering you have, the asymmetry parameter varies with cloud top height. So if you only have a single asymmetry parameter, then your retrievals of cloud thickness are going to have a height-dependent bias. And if you're trying to use those retrievals then to evaluate whether climate models are doing things right, height-dependent biases are really, really bad, because these clouds up here are much, much colder than these clouds down here, right? The rule of thumb is 6 degrees C per kilometer. So you go 8 kilometers, that's 30 degrees. And if you're biased the wrong way up here versus down here, that's going to be a bit of a nightmare if you then try to tune a model to something like that. And obviously the size also varies. And this is one of those things where we actually will be able to correct OCI, even if OCI has a fixed ice model, because we can just take 1 minus the asymmetry parameter OCI divided by 1 minus the asymmetry parameter retrieved, for example, from HARP2 and correct that optical depth. So we can fix that bias. Yep. We're going to see a lot of this. I just wanted to note that Peng Wang has a really nice model of the ocean body that incorporates polarization. My colleague Yatsik Chowdhury has one, and you can get the scattering matrices from him if you want to have a polarized ocean body coupled to a radiative transfer model. And I think that's probably all I'll say about that one. And then this is related to what Lorraine was talking about with dark targets. Just that the land surface, there's a correlation between longer wavelengths and shorter wavelengths, and you can use that in your remote sensing retrievals. And there are quite a few papers written on this, right? And Lorraine and Andy Sayer are the two experts on that area who will be attending this workshop. So if you're interested in that kind of characterization of the surface, you should ask them. And the other part of surface properties, I just wanted to throw this in just to provide a couple of references to spectral libraries. I don't think there are many land surface remote sensing people here, but if you're interested in land surface remote sensing, then these spectral libraries provide you with vegetation spectra and then mineral spectra. And obviously, OCI is giving you the spectra that are really good for vegetation and phytoplankton. People who are interested in mineralogy are actually more interested in spectroscopy out here, and so we're not going to be doing that. And then the same kind of, this is just showing how the 2250 polarized reflectance compares to 410, 470, 555, 670, and 865, and basically it's a one-to-one line. And what that means is this is a very gray picture of the polarized reflectance. This is a very colorful picture of the total reflectance. And it's just showing that the polarized reflectance is gray. And that's a really nice feature to have when you're trying to do remote sensing of aerosols, because you don't have to worry about the color of the surface. As I said, this is aerosol remote sensing. This is the merged dark target and deep blue product. And as you should talk to Lorraine and Andy if you're interested in more about how that works for MODIS and VIIRS and how that's going to work for OCI. And they're going to talk about that, the products then on in lecture 10. And then, so once you get the multi-angle, multispectral, ultraviolet, you can start to get into things like not just retrieving aerosol optical thicknesses, but also single scattering albedos and aerosol layer heights. Are you going to talk about your layer height and absorption at all, or is that not part of this? Okay, so Lorraine is working on doing aerosol layer height and absorption from OCI. Yep. And so this is just showing that this is showing what you can do with the multi-angle polarimeters, but Lorraine is also extending that to doing the same kind of thing with the single view full spectrum from OCI. Okay, and then so this is the end of the omnibus remote sensing radiometry. I'll leave you to read this and take any questions while I have a drink.
I have a question about the calibrating the instruments.
Sure.
I'm assuming they're pretty stable because they're going to space, and like in an ideal world, it's best to calibrate your instrument at the conditions. So when you're using the glamour, whatever it's called, do you do it at like very cold temperatures, or is it standard and it's okay to just
That's a really good question. There are instruments. So what you do with something like the PACE mission is you do calibrate and test at the temperature that the instrument is going to be operated at. And you get a calibration curve as a function of temperature over the expected operating range. So that's a sort of really nice way to do it. A lot of airborne instruments do not temperature control the instrument when it's on a plane. And so the calibration that you do at room temperature is usually completely useless if the instrument gets down to -20 or -30 degrees C. So yeah, you do need to calibrate at the same temperature that your instrument's operating at. And so for my instrument, it's all wrapped up in lots of insulation and got lots of heaters inside. And we try to keep it operating right around 20 degrees C. Unless the ER2 pilot turns the heaters off, which has happened. And that was a bit of a disaster. So yeah.
Also, when we go through thermal vac, you know, you're cycling your temperature like it would be on orbit. And during that, we're testing the baseline all the time.
Right. Yeah, so the satellite instruments, you do get that. Not all airborne instruments do it or could do it. You know, it's the sort of testing you get on satellite instruments is usually much more rigorous than you would be able to afford for an airborne or ground-based instrument, for example. Yeah, go ahead.
So I have a question about how do you design or determine the spectral response function for the radiometer? So why do they have that shape? How do they have that shape for different?
Oh, which one? The funky one? There. So you don't actually want, you don't really want this kind of funky business, but it's but what you do want is you want a narrow filter with strong cutoffs. And these are what are called interference filters. And what you find is that if you want a really good cutoff out of band, then you'll often end up with some structure in band. And it's just one of those things you have to live with. It's not particularly desirable. And that's why when you're designing these bands, you do want to be very careful. I guess the spectroscopy, yeah. You do want to be very careful about this, right? Because if you have some of that structure that's co-varying in a bad way with, say, something like the oxygen A band, that would make the band almost unusable. Yeah?
I have a question about the calibration as well, using the Glamour laser.
Mm-hmm.
I know that laser is, they talk about it getting stable to a certain radius. So I know normally you need to get some sort of like a line, a linear assault. Do you do, so that one laser radius, do you change the integration time of the instrument, or are you doing something else?
It depends on which instrument we're doing it with. You can actually, with the Glamour system, you can actually do both. So we calibrated the Specs 1 instrument on a system in the calibration facility, which was not that Glamour facility, but it's essentially the same. And they wanted to look at the linearity as a function of integration time. And so that's one of the things that they did, was they changed the integration time to look at linearity with integration time. The other thing you can do with that kind of system is you can actually change the power of the laser. So you can also ramp the laser power a little bit. And you have the NIST traceable radiometers looking into the calibration system at the same time, so you get that traceability. Another way in which people look at linearity is is if say you can get 3 power levels, you can also put in a glass plate, and that will give you a fixed delta in your transmission. So you'll have power at 3 levels and then a small delta at each of those levels, and you can check that the delta is the same at all 3 of the power levels to check the linearity over range. So those ideally you do all of those, but sometimes you run out of time. Any other questions? Okay. Can you kick off the specs one, Peng Wang? I think you might end up being lucky that this next lecture will be somewhat shorter because my voice will run out, especially if I try to do it with a Dutch accent.
5-minute break, Brad?
5-minute break would be good, yeah.